Physiological signals aren't just data points. They're the continuous, non-invasive output of complex, nonlinear dynamical systems operating inside the human body. Modalities like EEG, ECG, and PPG encode rich temporal patterns spanning milliseconds to hours. Yet most machine learning approaches treat them as static inputs for classification or short-horizon regression. This misses the core reality. Physiological signals are generated by evolving dynamical regimes, and their true predictive power lies in modeling how they transition over time, especially when clinical interventions are introduced. That's the gap we're closing with Normware 2, a latent world model designed specifically for physiological time series. Instead of predicting isolated future values, Normware 2 maintains an internal dynamical representation of the body, encoding multivariate signals and clinical action variables into a shared latent space. It then models their joint temporal evolution as a conditional dynamical system. The result is a framework that can forecast, simulate, and reason about physiological trajectories across multiple temporal scales, all while adapting to heterogeneous interventions. The architecture operates on two complementary inference pathways, intuition and insight. Intuition is the pretrained backbone. It leverages broad physiological dynamics learned during large-scale masked reconstruction pre-training. Insight is the novel component. At inference time, it performs instant, non-parametric latent state transition adaptation. The observed context is encoded into latent patches, clustered into discrete states, and their empirical transition probabilities are estimated directly from consecutive patch pairs. When clinical actions are present, the transition becomes action-conditioned, allowing the model to simulate how specific interventions alter physiological trajectories. But here's where the data curation strategy becomes critical. We discovered that standard pre-training corpora are heavily skewed towards specific dynamical regimes. Most datasets are dominated by quasi-periodic or weakly chaotic patterns, leaving the model underexposed to bifurcation regimes and strongly chaotic dynamics. To fix this, we quantify the chaotic properties of each time series using three metrics from nonlinear dynamics: the Lyapunov exponent to measure sensitivity to initial conditions, detrended fluctuation analysis to assess long-range autocorrelation, and persistent entropy to capture the topological loop complexity of the reconstructed phase space. We compute these metrics across the pre-training corpus, apply unsupervised clustering, and assign semantic dynamical labels to each cluster. Then we curate a dynamically balanced dataset. The empirical result is striking. A balanced corpus half the size of standard benchmarks actually outperforms them. Why? Because forcing the representation learner to navigate stable, chaotic, and transitional regimes builds more robust, transferable latent structures. When we test this on a paradigm system like the forced Van der Pol oscillator, the chaos-balanced model correctly identifies stable attractors and degrades gracefully only after the onset of chaos, whereas sensing-only models fail across all regimes. This proves that chaos-aware balancing isn't just a data hygiene step. It's a fundamental requirement for learning generalizable physiological dynamics. Let's look at the math behind the inference pipeline. After patchification and channel-aware encoding, the latent embeddings are grouped into clusters. The number of clusters scales logarithmically with the total number of patches. We estimate the empirical transition probability as the ratio of consecutive state pairs. Forecasting is performed by sampling the next latent state from this transition matrix, then drawing a continuous latent representation from the corresponding Gaussian component centered on the cluster centroid. When intervention variables are introduced, the transition probability is no longer state-only. It becomes action-conditioned. We marginalize over possible actions, or, more efficiently, use Euclidean neighborhood search in joint state action space. This restricts forecasting to transitions consistent with the observed intervention dynamics. We can also frame this as an energy-based model, where the energy function is defined as the negative log likelihood of the transition. Forecasting then becomes sampling low-energy transitions, which is mathematically equivalent to maximizing the likelihood in the corresponding Markov graphical model. After generating the desired number of future latent patches, they're passed through a lightweight decoder to reconstruct the output time series. The intuition pathway uses the pre-trained backbone directly, while the insight pathway injects context-specific transition dynamics. Together, they form a complete generative forecasting loop. To evaluate this properly, we can't rely on pointwise error alone. Physiological forecasting requires assessing temporal alignment, spectral fidelity, and semantic representation. We built a multidimensional evaluation protocol that spans 3 domains. In the time domain, we use mean absolute error and differentiable soft ETW to capture morphological consistency. In the frequency domain, we compute FFT cosine similarity and Euclidean distance to measure spectral component alignment. In the latent space, we extract pre-trained embeddings from both predicted and ground truth sequences and measure cosine similarity and Euclidean distance to assess high-level semantic consistency. These metrics are normalized and combined into a composite score that reflects holistic forecasting quality. We tested this across 5 real-world datasets spanning millisecond, minute, and hour-level resolutions. VitalDB covers perioperative surgical monitoring with ECG, PPG, EEG, and anesthesia machine parameters. PM data tracks daily wearable sensing with heart rate and activity. CG macros and Shanghai diabetes handle biofluidic glucose monitoring with meal and insulin interventions. Kidney dialysis provides hour-long hemodialysis sessions with physiological signals and ultrafiltration rate controls. Across all these domains, Normware 2 consistently achieves the strongest composite performance. It outperforms state-of-the-art time series foundation models like Chronos-2, T-Ray-X, Sundial, and Panda, particularly in long-horizon latent and frequency alignment. Statistical testing confirms these improvements are significant across temporal resolutions, sensing modalities, and evaluation metrics. The action-conditioned forecasting is where the model shows its clinical relevance. In dialysis, the ultrafiltration rate is the primary intervention variable. Clinicians adjust it to manage fluid removal, balancing symptom risk against treatment duration. We evaluated how the model forecasts systolic blood pressure under varying UFR settings. The predicted distributions remain tightly aligned with ground truth physiological ranges, and prediction error stays consistently low across diverse action-state combinations. The model learns the actual clinical trade-off. Reducing UFR stabilizes blood pressure and reduces adverse symptoms. We see similar action-aware behavior in diabetes management, where insulin administration and meal composition correctly shift glucose trajectories, and in daily wearables, where activity changes modulate heart rate dynamics. We also tested personalization scaling. By feeding the model increasing amounts of subject-specific historical data, forecasting performance improves monotonically across all temporal resolutions. The latent transition mechanism effectively leverages accumulating user history to refine state action mappings, showing strong potential for continual improvement in real-time monitoring deployments. Additionally, the transition modeling framework is backbone agnostic. We integrated it with univariate transformers, CLS attention architectures, and JEPA-based models, and each saw significant, consistent gains. This confirms that the dynamical state transition module is a modular enhancement that elevates temporal representation learning across different architectural paradigms. There are limitations, and they point directly to the next phase of research. While Normware 2 captures action-conditioned dynamics through latent state adaptation, it doesn't yet operate within a formal reinforcement learning framework with explicit reward optimization. Real-world clinical decision-making requires optimizing long-term outcomes under uncertainty, where actions should be guided by well-defined objectives rather than implicit adaptation alone. Extending this latent world model to support policy learning over discrete latent states, trained to optimize clinically meaningful rewards, is the natural next step. This work shifts physiological AI from static representation learning to dynamic, intervention-aware world modeling. By combining chaos-theoretic data balancing, non-parametric latent state transitions, and action-conditioned forecasting, we've built a framework that doesn't just predict the next value, but simulates physiological trajectories under different clinical scenarios. It captures spectral structure, preserves latent semantics, and adapts to real-time interventions. For digital health, continuous monitoring, and personalized medicine, this is a foundational step towards systems that can reason about the body as a living dynamical system. The code, pre-training data, and checkpoints are publicly available, and the path forward is clear. Integrate these latent dynamics into formal policy optimization, and we'll move from forecasting physiology to actively managing it.